Okay, get ready for this. What if I told you that the way a drop of ink spreads out in a glass of water shares the exact same math as an AI creating a stunning picture of an astronaut riding a horse? I know, it sounds totally bizarre, right? But it's not some loosey-goosey metaphor. It is literally the same mathematical framework. So let's dive in and see how this actually works.
So on one hand, you've got physical diffusion. You see it every day. It's how things in the universe naturally spread out and get more chaotic. And on the other hand, you have this incredible AI technology that takes a simple text prompt and creates something with incredible order and detail. I mean, they seem like polar opposites, right? One creates chaos, the other creates structure.
So, what's the deal? How on earth are these two completely different worlds connected? How does the physics of things falling apart become the secret recipe for creating mind-blowing digital art? Well, that's the big question we're going to tackle right now.
Look, in AI, we hear a lot of analogies, like comparing neural networks to the human brain, and honestly, a lot of them are a bit of a stretch. But this one's different. Diffusion models are, for real, built on the mathematics of physical diffusion. And this all comes from a pretty specific field of physics.
That field is called non-equilibrium thermodynamics. It's basically the science that describes how stuff, spreads out. Think particles moving from a crowded space to an empty one. So just hang on to that core idea of particles dispersing, because it's going to be the key to unlocking this whole thing.
To really get our heads around this, we need a good way to visualize the problem. So let's imagine the entire challenge of making an image isn't a computer science problem, but more like a geography problem.
I want you to picture this enormous, practically infinite landscape. Every single point in this landscape is a unique image. And I mean every possible image, from a perfect photo of a cat to a screen full of just random static noise. It's all in there somewhere.
Now, this landscape isn't flat. It's got hills and valleys, and they're defined by probability. So the hills, the peaks, those are the spots that represent real coherent images, things that actually look like something to us. A car, a house, a person. These are high probability areas. And the massive, flat, empty valleys, that's just meaningless noise, low probability region.
So, when you think about it, the goal of an AI image generator is actually pretty simple. All it has to do is start somewhere down in one of those noisy valleys and find a path that leads up to the top of a hill. If it can do that, bam, you've got yourself a brand new structured image. But of course, there's a huge catch.
And here it is. The crux of the problem is that we have no idea what this landscape looks like. It's just too big, too complex. All we have are a few examples of real images, which is like having a few flags planted on a handful of hills in a landscape the size of a continent. We don't know the shape of the terrain at all.
But here's the genius idea. What if you don't need a full map? What if, instead, you could build a kind of magical compass? A compass that, no matter where you are on this landscape, could always point you in the direction of uphill, towards a more image-like image. Well, that is exactly what a diffusion model is trained to be.
So how do you build this compass? Well, paradoxically, you have to teach the model what the landscape feels like by taking beautiful, perfect images and systematically destroying them with noise. This is our first journey, from a clear image all the way down into pure chaos.
So here's the process. You start with a real image. That's like our particle sitting right on top of a hill. Then, step by step, you inject a tiny bit of random noise. That's the diffusion. You can just imagine that particle slowly rolling downhill, going from that structured, high-probability state to a completely random, noisy valley. You do this millions of times, and you record every single path. That becomes your training data.
And the reason for doing this is just so clever. Adding noise is like spreading out the hills. See, real images are incredibly rare in the grand scheme of things, so most of our landscape is just flat and boring. By diffusing the images out, we're basically creating gentle slopes everywhere. That way, no matter where our AI starts, our compass always has a gradient it can follow.
Now, this journey from a clean image down into noise isn't just random chaos. It's actually described by a very specific mathematical tool, a stochastic differential equation, or SDE. Just think of it like a recipe for movement, and this recipe has two main ingredients.
The first ingredient is the drift term. That's a predictable force, like a gentle pull that guides our little particle in a specific direction, in this case, towards the center of that noisy valley. The second ingredient is the diffusion term. This is a random jitter, kind of like the chaotic way pollen grains dance around in water. You put those two together, and you have a perfect mathematical way to destroy an image.
Okay,
So we have spent all this time teaching our model by showing it millions of paths from a clean image to total noise. Now comes the magic. We're going to reverse the journey. We start with pure random noise, and we use our train model, our compass, to find the way back to a beautiful, structured image.
At this stage, our model has basically learned the slope of the landscape. So you can give it any jumbled, noisy mess, and it can predict the exact tiny step it needs to take to make that input just a little bit less noisy, and a little bit more like a real image. It always knows which way is up.
But wait, we can't just climb the steepest path to the absolute highest mountain peak, right? That would be an optimization problem, and it would mean the AI generates the exact same perfect dog picture every single time. We want variety. We need what's called a sampling algorithm, something that can find any of the valid dog hills and pick one at random. And this is exactly where diffusion makes its comeback.
It turns out that whole diffusion process is mathematically reversible. The researchers figured out a reverse SDE that acts as the perfect recipe to travel backwards. It uses our compass, the model's prediction, for that predictable drift, but it also re-injects just a little bit of randomness at each step. This lets it wander around the landscape and settle into any one of the many, many different plausible image peaks. So we have this incredible, mathematically solid framework. But there's one last huge practical problem. This reverse journey is super duper slow. And that brings us to the final innovation that really made all of this possible for everybody.
Because that reverse path is so jittery, remember we're adding randomness back in, it needs a ton of tiny little steps to get a good result. We're talking something like 1,000 steps, which could take minutes just to generate one single image. Totally impractical.
But then, researchers had a breakthrough. They realized you could remove the jitter entirely. They found an equivalent deterministic path described by an ordinary differential equation, or ODE. This path is smooth. It's predictable. And because it's so smooth, you can take much bigger steps along the way without losing your footing.
And the difference is just staggering. Instead of 1,000 steps, we can now get a fantastic-looking image in maybe 25 steps. That's a speed up of more than 20 times. And that is the key that turned this from a slow research project into a tool that literally millions of people can use every day. It's what makes things like stable diffusion even possible.
So there you have it. We started with the physics of how particles spread out, and we ended up with a compass that lets us navigate a landscape of pure imagination, literally creating art out of chaos. But this whole thing relies on the idea of a continuous space where pixel values can be anything, which leaves us with one last, really fascinating question. How does language, which is all about discrete words and tokens, fit into this very physical, continuous formula? But that is a story for another time.